I'm going to present some high school mathematics applied in a very ingenious way, in my sense of it. This is a discovery by two high school girls from New Orleans, Calcea Johnson and Nakia Jackson. And they discovered, using pretty much whole brain approach, there's linguistic skills involved in mathematics, especially in writing mathematical proofs and communicating about it, and a lot of spatial and geometry, algebra, geometric series was used in this proof. And the brilliant part was that many people thought was impossible was the use of trigonometry to prove Pythagorean theorem. And the reason why that was thought to be in question was because people just automatically think Pythagorean theorem is just based on our trigonometry, which is kind of an accounting system for right triangles and the proportions or ratios of the sides in right triangles that you can make tables for, and you can also have an infinite series for to calculate as accurately as you want. So most of the results are well, that's the thought that people had as syzygy, but the law of sines is independent of the Pythagorean theorem, and they use the law of sines, which is from trigonometry. And I'm going to show you how. And I'm going to try to avoid getting too much into the details of the derivations. I have all the derivations that you need written out in this. And I have a note card from the time when I presented this. This was presented in Maths Club to our handful of true interested people. Not that the people here today aren't interested, but at least interested in my activities up there on the 6th of February. So in about 10 minutes more, I'm going to share the note card from that day, and it has a link to a PDF for all these slides that I'm going to show. And so I'm going to try to keep it kind of to general points and not get bogged down by the details. You have to really dig into well, the trigonometry identities. Let me show you. You're right. The trigonometry identities certainly reflect a Pythagorean theorem in that, but the sine law of sines I'm going to show you is independent. So let's dig in. The law of sines. What is it? Well, it's the fact that any triangles, 3 points determine a plane. 2 points determine a line. 3 points determine a plane. 3 points could also lie on a curved surface, but we're assuming it's a plane, a Euclidean plane. So any 3 points as vertices determine a triangle, and you take any such triangle in the universe that's in a Euclidean plane. And if the universe has curvature, or an area that has curvature, if you take a small neighborhood around an area, around a point, a small neighborhood, meaning like an open, like a ball with no skin, just a fuzzy ball that doesn't include the the shell of it, all the points around the center. That'd be a neighborhood. That's a common concept of a neighborhood in topology. So you take a small enough neighborhood and things get linear. They get flat, like Euclidean geometry. We're going to assume just Euclidean geometry. So the fact is, you take any triangle such as we have drawn here, and you have labels for the sides A, B, and C, and alpha, beta, and gamma, where I have it as by convention so that alpha is the angle opposite of A, beta is the angle opposite of B, and C is opposite of gamma in this case. Um, the well, you look at these ratios here that I have written. Sine of alpha over A is equal to sine of beta over B is equal to sine of gamma over C. Is also equal to 2. This is the one, the part of it that people may not have seen in high school. 2r, the radius of a circle that circumscribes the triangle. And let me just mention what that means. If you have any triangle and you take bisectors of the sides, you can just do 2 sides. If you want to be OCD, I tend to do this. I tend to do, if I try to construct one, I tend to do it from every single corner, because then I've got a sampling of 3 lines and see if they cross all at the same point. And it basically is a test of how good my construction is. But the intersection point for these midline bisectors that are perpendicular to each side is, and we're going to kind of confine our attention to acute triangles here, is in the center of the triangle. And if you take that point and put your compass to any vertex on the triangle and make a circle, it will touch all 3 vertices. It will circumscribe your triangle. A beautiful little thing. I remember when I first started this may be distorted, but what I would ask you is look at the pictures as a guide and perfect them with your imagination. In geometry, images are, I know I can't help that. It doesn't, when I make it on PowerPoint and make the slides, when I upload it here, it looks oval. Just to show, I'm not going to fully prove the law of sines. For one thing, this is just for an acute triangle. If you want to prove it more completely, you'd have to look at obtuse triangles where one angle is greater than 90 degrees. If you drop a perpendicular from one vertex, which we call H, and you have then 2 right triangles, and you have your definition of sine of alpha and sine of beta that you can work off of. And from those, you can get a value for H. H equal B times sine of alpha, and H equal to A times sine of beta. And then equate them, and then you're working with A and B not equal to 0, so you can divide both sides by B and both sides by A, and you'll get sine of alpha over A and sine of beta over B. It has no demands from the Pythagorean concepts to prove this. And you can apply the same angle to all 3 internal angles to get the equivalent result. You can prove it for another couple of angles, and if it works for angle alpha and angle beta, and it works for beta and angle gamma, then it would work for angle alpha and gamma by kind of a transitive argument. So let me take a second at this point to share the note card, if I can find it quickly, from the um, let's see. Here we are from the 6th of February. And I'll share that with everyone in the room. And like I say, it has, here we are, it has a PDF on it, a link to a PDF that's in my Google Drive. I guarantee it's safe for your computer. And let's see, I'm going to maneuver things around here. Okay. If anyone else shows up, if somebody could share the card with them, I would really appreciate it. Everyone gets a card now, I hope. It looks successfully shared. So we have to look, great, thank you. We have to look at what the situation is if one of the angles, let's say gamma, is a right angle. The sine of a right angle is 1. If you look at the lower left-hand corner, this is an ovalized or ellipsoid or elliptical squished circle, but it's think of it as a unit circle. And I have the base and the height in a red line and an angle theta. And the white line is the hypotenuse. The vertical line opposite of theta in that lower left-hand corner diagram is the sine of the function. And think of it as that theta gets larger and larger. The red vertical line will get closer and closer to the length of the radius. And at 90 degrees, or pi over 2 radians, as is used more in mathematics. Thank you, Phoenix. Appreciate it. The sine of 90 degrees will be seen to be 1. That's quite useful here because we can apply that here, and with sine of gamma being 90 degrees, since we're going to be talking right angles, and end up with the law of the sines as sine of alpha over A is equal to sine of beta over B. This is in the black box up the right-hand corner, is equal to 1 over C. So we don't have to worry about a sine function there. It simplifies itself a little bit. And maybe more importantly, and I should have done this earlier when I wrote these out, is take the reciprocal. It's the same as saying A over sine of alpha is equal to B over sine of beta is equal to C. So we'll discuss that again in a few moments. So, yeah, but we don't have to worry about cosines because it doesn't pertain to this proof. Yeah, you can always talk more about other things here. I'm trying to, for one time in my life, I'm trying to stay focused and not be everywhere, trying to do everything all at once, as they name the movie or something like that. All right, the proof applies only to right triangles for which two sides are not equal. So the tricky proof, anyway, if the two sides are equal, we need to look at that case real quickly. Everything, everywhere, all at once. I was thinking I'd permutated the order of the all-inclusives. So if you have a right isosceles triangle, the black little, I have two yellow lines that say A. One looks longer than the other. That's not my fault. That's Biden's fault. At any rate, they are intended to be equal, and the angles the base angles in an isosceles triangle is, yeah, I don't know how to do that. To change the aspect ratio. The isosceles base angles are both alpha if the sides are equal. That's easily proven. That's also not dependent on Pythagorean theorem. So in this case, if you imagine, that alpha, sine of alpha, where alpha is equal to 45 degrees, is square root of 2 over 2. If you knew that already, then it would be easy to show that the Pythagorean theorem works. And that's sort of what I did here. There you could get me maybe, because you'd have to figure out a way to show that the sine of 45 degrees is equal to 1 over square root of 2, or the square root of 2 over 2, which is equivalent. One way you can do this is look at the lower left-hand corner. If you make a perfect square and kind of de-aspect it to look like a perfect square, and you make diagonals, it's easy enough to show the diagonals would have to cross at equal angles, and the bisections, or the way the diagonals cut the angles at each corner, would have to be equal. So you can end up looking at 4 isosceles right triangles, or just 2 if you want to keep it simple. I think I did it with 4, simply because that's what I wrote out. And I have the calculations here in the lower right-hand corner. That's to show that if you take from a fundamental philosophical concept, the total is equal to the sum of the parts. You add up the areas of the triangles inside, and it should equal the area of the square that contains them. And in that case, it's a squared is the area of the square, and the 4 times the 1/2 c over 2 times c over 2, since the height and base of an isosceles right triangle is the side, and the side is length of c over 2 in that case. And we're talking about these basically quarters. I could have maybe made it easier. Definitely would have been easier to just do the 2 triangles. I'm always looking for harder ways, So it's easy enough to prove a Pythagorean theorem with an isosceles right triangle as a special case. So that leaves us with our challenge of creating a proof, which is going to use trigonometric concepts, the law of sines, that are independent of the Pythagorean theorem, to prove the case in which the right triangle is not an isosceles right triangle. In other words, where one of the sides is greater than the other side, or less than the other side. And by rigid transformations, you can rotate and you can flip. You kind of invert the triangle, as just like flipping a plane, or just rolling it over. If you took this triangle on the left and rolled it across either A or the A line, or like a rotation, like you pulled the alpha angle out towards you and then lay it down from your right to the left. You could then rotate it in the plane into any position. The point here is that if you have one side that's longer than the other, you can put the side that's shorter wherever you want it. And that's actually important to this proof. Just to get that straight, just for Leibniz wrote about how if you can just put your symbolism and write things out in a certain way, it almost seems to solve itself. And so in mathematics, one of the tricks is being able to see what is, you can arbitrarily choose as representation, and proper representation will make your life much easier. Yeah, I saw about the flipping the plane. I saw a joke that said about Senator Federman of Pennsylvania that uh, if a plane flips from now on, they should call it a Federman. Probably shouldn't have told that joke. Anyway, yeah, that was terrific. They got everybody out of that plane. But anyway, back to this. I'm very distractible. I had caffeine this morning because I didn't want to take time to make my decaf, and caffeine hypes me up. Maybe too much. So, any questions about this so far? Any comments? We're good. Everybody good? Okay. Now, let's see. I got something right. Something popped up in front of my view of my screen. If you've got any given right triangle of sides A, B, and C, we also need to note that sine function is strictly increasing between 0 and 90 degrees. If you look, the orientation isn't great, but if you look at this alpha in the left-sided triangle, or well, look at beta. Look at beta on the right. Let's look at the right triangle where you have the vertical B over C is the sine of beta. And let's keep C equal and imagine from the lower left-hand corner making an arc so that you're seeing what happens to B. B gets longer and longer until it reaches the value of C as beta grows. They are interchangeable, but I'm showing that you can consider one case and you can flip the other around or maneuver if it happens to be a B. If it's not an isosceles right triangle, then A has to be greater than B or B has to be greater than A. And what I'm arguing is that you can take just one of those as your working format and apply it, and then you know automatically that it would apply if you had the B greater than A, because you can do rigid transformations, or you could replicate your entire proof with your orientation having the other side being longer. But no, I think I worry a lot about the world right now, so I understand that. Anyway, this concept of sine a function being strictly increasing from 0 to 90 degrees, actually, that's not I could make that more general, but we're only interested in 0 to 90 degrees for this. That's important. I'm going to show you a little bit more about that in a moment. Since it is strictly increasing, except that for the moment, if you don't quite buy it, if A is less than beta, then B, then alpha, sine of alpha has to be less than sine of beta, and because C is used as a denominator for both, and C is positive, so you can buy A over C would be less than A over B. A over C would be less than B over C, which means sine of alpha would be less than sine over beta, than sine of beta. And because it's strictly increasing, you can say alpha would have to be less than beta. Or if it were the other way, it would work out that alpha would be greater than beta if A is greater than B. It's just they move together in a sense. They don't move linearly together, but they move together in terms of their growth and their values. If A is greater than B, you have A over B is greater than 1. Now, I looked at this a few minutes ago, and I was trying to get my head right, and I realized that this drawing for that dotted purple enclosure doesn't look like the drawing at all. It doesn't look like I even tried to make it, and I didn't. I just put that in there. But don't worry about if that applies to this triangle. We're going to get to something else that's where the triangles will make will be pertinent to the proof. But if A is greater than B and A over B is greater than 1, you can use the law of sines and show that sine of alpha is greater than sine of beta. That's all that shows. If anyone has a question about validity of that, I would recommend looking at the PDF and convincing yourself of it. Here is a graph. You can go to Google browser and type in graph sine x. I use it all the time to make graphs. And so I used it for this, just made a sine function. Everybody's seen sine functions. And I pointed out this shortened domain 0 to 1, 0 to pi over 2. The angle for graphing trigonometric functions is generally in radians. It's related to the arc length over the length of the radius. And if you're in a unit circle where the radius is 1, then the angle is simply a measure of the arc subtended by 2 rays that come from the origin. So anyway, I'm pointing out the red is the beginning and the black the end, and you see that the sine as you go to the right just grows. And I have a close-up of it here to the right. So that will let people co-sign onto this idea that sine function is strictly increasing. Okay, now for our proof. We're doing well with time, I think. Any questions? Yeah, do not try this at home. Actually, do try it at home. One of the things I always liked about mathematics is that if I could internalize it, and one of the nicest things about it is that you can just remember an idea, a concept, and you can figure almost anything out if you think through it right. But you could be in prison, and if I imagined myself ever in prison, I'm going to tell them I know how to make explosives, and I'm going to tell everybody how to do it. And so I'll be put someplace, I'll be left alone by myself. They'll keep me in solitary. But I'll deal with that. I'll just think about things like mathematics. Or if I were on a desert island, I could reconstruct much of civilization or the ideas of civilization out of my head just by having a sense of the ideas. Mathematics is beautiful that way. So, at any rate, let's that aside. Let's start with the upper left-hand corner. I tried to use small, like Roman numeral steps here for step I. Start with the right. That's a great joke. Sumo. Start with a right triangle, sides A, B, and C. We're all happy with that. It's well labeled. The A side is opposite the alpha angle, the B side, is longer than the A, that's the way we choose. If it were the other way, we'd flip it around so that we could have the longer side going vertically. It's just convenient, trust me. Opposite of the vertical B is beta, and the hypotenuse is C, and a little right angle indicator there in the lower right-hand corner. So follow the, and so we're assuming A is less than B. Roman numeral 2, construct a second right triangle. And yeah, the Alcatraz is, I've been on Alcatraz. It's an interesting place. Kind of rustic and pretty almost. Anyway, construct the second right triangle with sides A, B, and C that's perfectly congruent to the first one. So you put them back to back, and so you have at the top, your angle is going to be 2 times alpha. You have alpha to alpha. And the base is going to be of length 2a. And the base corners, this is now an isosceles triangle, and the base is going to be beta on each side. And since this is a right triangle, beta is definitely going to be less than 90 degrees. Anyone have any question about that? Alpha and beta are both less than 90 degrees because there's some being part of being complementary angles in a right triangle. There's some with the right angle has the equal 180 degrees. So you've got the right triangle that counts for 90 degrees. So the alpha plus beta have to total 90 degrees. So if they're both greater than 0, neither of them can be 90 degrees. That's an interesting point to keep in mind. Okay, so we've got that set up. And let's see, I maybe have already talked through this. So you've got your base 2a, and your the cap angle is 2 alpha. And equal sides C and base angles beta. Now step 3. You use the law of sines on the isosceles triangle because you have 2 relationships. One is you have the sine of beta is equal to B, the vertical, over the hypotenuse C on the smaller right triangle. And for the isosceles triangle, you have 2 alpha, sine of 2 alpha over 2a. Over its opposite side is going to equal to sine of B over C. Because in the bigger triangle, sine of beta, the beta is opposite C in the larger isosceles triangle. This is what these 2 high school students did. This was very smart. This was a very smart critical step in this. And yeah, wait till you see where they used like everything. They threw the kitchen sink at this thing, and it's just really clever and beautiful. Yeah, absolutely. My hat's off to them. And we'll talk a little bit about them and what they're doing now in a bit. But so you've got this relationship that you can derive. That's I put in a yellow bar, a yellow envelope or whatever. In the upper right-hand corner. That's what I'm deriving here in these 1 through 5 statements. So take that and we're going to run with it. Remember that key relationship. And so looking at this, this is not a critical point, but if it happened that 2 alpha were pi over 2 equals 1, then from that you would also have easy validation of the Pythagorean theorem for an equilateral right triangle. Just an interesting note. But let's go beyond that. Let's do something interesting. Let's extend the side on the right of our isosceles double triangle down to wherever it goes, and let's go down to the lower left-hand corner of our double right triangle, our double isosceles triangle, and this orange line, you got a kind of a salmon or a pink or something line to the right. I tried to make the color coded so I could talk about it. Yeah, we're getting pyramidish, and we're going to walk like an Egyptian through this. So you have this orange line that goes from the beta angle on the left down to wherever it goes, and that is a right angle. It's going to meet we can construct a right angle off any line segment. We could extend C on that left side and use a compass and make a couple of arcs from the vertex of the isosceles triangle, and then make arcs on either side of it that would cross to give us 2 points to create this line. So this is a constructible line, and it will always intersect this other line because the beta, but because they can't be parallel, I guess is the thing to say. For this to be parallel, the 2 alpha would have to be equal to pi over 2. The 2 alpha would have to be 90 degrees for the two constructed, the extended line and the newly constructed line to be parallel. And 2 alpha has to be less than 90 degrees because alpha is less than beta. Everybody buy that? That's actually an important little point. And so to continue, we will call our orange line on the left X, and our line from the top, from the cap of our isosceles double triangle to the intersection point Y. And whoops. Just for, I'm going to call Y sub S, this segment that is the extension, I'm going to call Y sub S. And with that, we identify this where we can have the law of sines, the sine of 2 alpha, which is at the top, over X, because now you have a bigger triangle, bigger right triangle is equal to 1 over Y, because Y is the hypotenuse. Y is the side opposite the right triangle that you constructed. So you get this relationship, X over Y is equal to 2AB over C squared. So if you could just know what X is and Y is, you can have a relationship to A and B. Okay. Any questions there? Keeps jumping. It's probably my fault. Whoa. Oh, man. It's going to take a moment. I'm sorry. These are all the slides that I have. All the slides I've used so far this year in Maths Club on one projector. I just add to them each week. This is from Thursday night when we talked about Euphemia Haynes, who was the first black woman in the United States to get a PhD in mathematics, and Albert Cox, who was the first black gentleman in the United States to get a PhD in mathematics. He got it from Cornell. This, by the way, is a statue called To the Stars. It's bronze, and it's from the USSR. I have one. I own one of these. And I asked in Maths Club, anybody know what that is he's holding in his hand? This Promethean figure in the left-hand corner, left side. Anybody know what that is he's holding in his hand? I'll tell you, it's a rocket. And he's launching a rocket to the stars. And it's a commemoration of Soviet achievement in space, which was quite substantial. And here I talked about Benjamin Banneker, who was a freeman in colonial times, who is sort of comparable to Ben Franklin, and then Thomas Fuller. This is the door of no return in Benin, where the slaves were taken after they'd been kidnapped, taken down to the slave ships to never see their families or their homeland again. So that's what people are referring to when the word 1619 comes up. Okay, here's my talk. I'm sorry for this delay. You see what's to come here. I don't know how it flipped to the beginning. I'm sorry of that. Okay, I think, yeah, this is where we left off. So we have this identification, and we create a waffle cone where we go to the right corner of our isosceles double triangle and drop a vertical perpendicular. And until it intersects the x, I don't have x on the left and the y sub s on the right. I don't have them identified here that way, but I wanted to keep it simple. And from that point where it intersects, we draw a parallel to the base of our isosceles triangle. So we draw where it intersects y sub s, we drop another perpendicular and then another horizontal, and stair steps that get smaller and smaller. Now, here's the beautiful thing. You look at the character, like just look at what you think the areas of those things, those triangles might be. Does it make you think of a geometric progression? There are geometric progressions hiding in this. So let's start with our top here. We have 2a at the top of this, our first layer below our double isosceles triangle. We have 2a is the roof. And we have has to be alpha is the upper left-hand corner angle, because it's a right angle, and the other angle to which it complements is beta. So it has to be an alpha. That means that the lower right-hand corner of that first large right triangle that was created is a beta. And then you have a right triangle, and if you look just based on parallel lines and the internal angles from the double isosceles triangle, you have a beta at the corner. And so this is a similar triangle, a similar angle, and it has to be beta. and then the other one has to be alpha. And you can do this argument progressively for each of the smaller and smaller, um, well, you're going to see, um, for each of the smaller and smaller triangles, so that you map out the angles. And if you know the angles, you might just be able to use the sine law. I'm sorry. So further mapping this out, what we need to do is to consider each section. And because each section is going to be similar to the one above it. It may be scaled differently, but they have um, congruent angles, corresponding angles. So, does everyone see that? That's also a beautiful observation from a beautiful construction. And so here's again our law of sines, and I point out again, if pi over 2 or 90 degrees is gamma, then it's equal to 1, and we have just emphasized that um, um, the C side becomes just C. It doesn't have to be over a sine. It's a simpler relationship. So looking at section by section, the C side, yeah. You have these, I don't want to say truths are self-evident, but it comes to mind. If you look at the box on the right, and what I have on the left is basically stating what we've already established, that the height of the section, this is just one of these many sections, and they're countable. You can enumerate them with the natural numbers. And so I put a sub in, and of course, I guess the first B is going to be 2A, you see, because if you look at the first B is the roof of that top right triangle that was constructed underneath the isosceles double triangle. So 2A is the roof of that. So that'll be the first B value in the first section. So anyway, you have the height over sine of alpha, since it's opposite of alpha, is equal to xn, which is a hypotenuse. Since you don't have to worry about it, it's a right angle, you don't have to worry about it over something, it's just equal to it. And you have bn over sine of beta is equal to the hypotenuse as well. So you can set those equal. Or you can manipulate it to find the value for hn. And you can do the same or similar equations for the right triangle on the right side that's smaller. And then you come up with these values, and you plug and chug. And I put stars. You can work your way through this. It'll take a lot of time. And if I had a chalkboard and you guys were taking a class and this, I would work through the equations on a chalkboard for you, but or whatever is used these days. But I put stars. I'll let people go to the PDF and just look at the equations to see that they work and that their derivations are right. You have a value for xn emerge, so that it's equal to this base at the top, the roof or the floor of the section, times this ratio. And then equation 6 is the similar derivation for yn. So you want to figure xn and yn, and Then let's see what happens with these. Whoa. Okay, so I just simplified it there. So you have yn is equal to a over b times xn. You can get a proportionality derived for the value of the right side to the left side, which is because of the law of sines, which is based on proportionalities and not on Pythagorean theorem. So if you could add up all these x values and xn and yn, get the length of x as the summation of all those, and the values of y sub s as the summations of all the y sub n's, then you could maybe equate it to y sub s is equal to a over b times x. X being the long right angle constructed line that was orange, that this is xn is a portion of, and y sub s being the extension of the right side of that double triangle. So, at any rate, I thought it'd be interesting to generate some tables using an initial value of b1. So I did that. And I think this is useful, not to clutter your mind, but it shows you, if you look at it, there's a common ratio in each of these. In the middle one, where it's xn, there's cb as a common factor, but you have a, and 2a is a common factor, but you have a squared over b squared as a common ratio, and in 2 you have a squared over b squared. In line 3 you have a squared over b squared times itself twice under xn, under the middle column there. In 4 you have it 3 times, and so forth. It grows in a geometric fashion of a geometric progression. Same for yn. And if that's the case, you can then apply the concept of geometric series to figure, and it's an infinite geometric series, to figure out what the summation of all those little lengths are. And I put this just to be a reminder of how the geometric series is derived. It's really pretty easy. It's a nice, beautiful little trick. Just multiply by the common ratio and then subtract the two and solve it for the sum s. And if you have a common ratio that is less than 1 and greater than 0, and it's you take larger and larger powers of it, it will converge to 0 as you go with the exponent toward infinity. So I have a small n here, and I put a large n for my, I should have put a large n there for my limit on that bottom line, but that's the equation for geometric series. So we apply that to our function, to our values that we had gotten to for each segment that gave us this relationship for xn and yn. So we want to figure out xn and yn. And we note that y sub s is equal to the whole y value minus the original c side, where they find the seashells, yeah. And so we come to this equation here that, and I put a star at it, on it. And do you notice it's starting to look familiar? It's starting to get kind of familiar components to it, like a squared plus b squared. And we take that a little further, And like in the upper left-hand corner here, we have validated that x is equal to this um, 2abc over b squared minus a squared, and the full length of y is equal to 2a squared c over b squared minus c squared, and take the ratio, and that's known uh, it to be 2ab over c squared, and I shouldn't be just reading these, but at any rate, you're able to equate your sum, and you end up with this situation where you have 1 over a squared plus b squared is equal to 1 over c squared. And therefore, since a and b and c are none of those are 0, and then you have from your original triangle that you have done all these funny things to, a squared plus b squared is equal to c squared. And ain't that beautiful? Ain't that beautiful? And so here's these sweet young ladies. And Charles Barkley was so impressed, he gave $1 million to their school. They went to this, it was a Catholic academy in New Orleans. And I'm sure they're very proud of him. And in Mass Club, I talked a little bit about how a ship's captain was a Calvinist minister named Job, who brought the first slaves to the colonies, American colonies, in August of 1619. He was a privateer, which is another way of saying pirate, and had taken them from a Portuguese slave ship. And they spoke Bantu language. They were from probably Angola area. It began with 350 Africans, and he ended up with 20 human beings, and I don't know how many. I guess in Veracruz, Mexico, they had 147 left alive. They threw them overboard as they died or got sick, because they were afraid the others would get sick, or they didn't want to waste food on the ones that were dying. So that's a lot to take in. But for these young ladies, I'm going to wrap this up because it's 2:01. Where are they now? Miss Jackson is a student in pharmacy at Xavier University, which is a nice school in New Orleans. Xavier and Tulane are there, as well as, I guess, Louisiana State University. There is LSUNO, Louisiana State University in New Orleans as well, but I think Louisiana State University for Miss Johnson is in Baton Rouge. And so I actually spent a reasonable amount of time in Baton Rouge and New Orleans. I was actually in New Orleans quite a lot when I was a teenager hanging out. I knew the French Quarter real well, and I was something what you might call a survivor type, and I also didn't do drugs because I felt like the only thing I had was my brain, and so I was afraid of frying my brain. But French Quarter is a tough place. New Orleans is a tough town. I had a friend when I was a teenager. I went to Mexico with a friend on a trip, basically to look at ruins. Everybody thought we were going for drugs, but like I say, we didn't do drugs. I didn't do drugs. But we went in to see all these Aztec and Mayan ruins all across Mexico. And that was one of the big adventures of my wayward youth. And my friend was shot to death in a truck at a stop sign in New Orleans. No, this was in the 1960s. I was down there. And I spoke pretty good at street Spanish. So anyway, they're both moving on in their lives. When I was thinking particularly with Miss Johnson with environmental engineering, she would probably be an excellent asset for any organization because she would probably be able to do computational mathematics and modeling of complex systems. And I worry personally in Nakia Jackson, individuals of this intelligence. Pharmacy's to be a pharmacist is a wonderful profession, but it's not exactly exciting most of the time. It's very detailed oriented and routine, and you explain the same thing to people a million times, and yeah, it's a good work, and they do good work, but it's so repetitious. I wonder if with her abilities, if that's going to be something she'll be happy with. And so I think it is a wonderful thing that we live in a society where at this point, black people can be educated without criminal offense being raised. It's in most all of the southern states, especially after Nat Turner in 1931 had a slave uprising. And they made laws to forbid. They didn't want the slaves to be able to read about abolition and want to escape to be free. And these were human beings, and human beings that are have their descendants among us. And there's in any group of people, there's quality, and if given the opportunity, they can contribute. 1831, I may have said the wrong century. I meant to say 1831 was Nat Turner, because supposedly we were emancipated in 1865 or 1864, the Gettysburg Address. That you had Jim Crow that went right up to the 60s, which was repressive. And one point about the Albert Cox, who got his PhD in 1925, there were, I think, 28 black men who got PhDs in one field or another that whole year in the United States. But it was unfortunate that in the United States of America, there were 31 black men who were lynched in that same year, 1925. So it's been a long journey. And I hope I haven't awakened anyone here with this kind of commentary, but this is Black History Month, and I think there's a reason to honor that and observe it. And so I wanted to bring that to Science Circle today. And that's the end of my talk. Any comments? Thank you for indulging me to 207.